On August 15, 1977, a radio telescope in Ohio detected a signal so unusual that the astronomer who found it circled it in red pen and wrote one word, "ow." The signal lasted 72 seconds, matched the exact frequency associated with hydrogen in deep space, and was 30 times louder than background noise. It has never been detected again despite decades of attempts. If a signal from deep space in 1977 still remains unexplained, that is the kind of universe this channel covers. You are watching The World Framework. Subscribe and do not miss what comes next. The original Big Ear printout from August 1977 presents a row of cryptic characters, 6EQUJ5. Each symbol records the signal's strength as the radio telescope swept across a fixed patch of sky for exactly 72 seconds. Numbers and letters serve as shorthand for how many times above background noise the signal registered, with the sequence mapping a sharp rise, a peak, and a fall. 6, then E, then Q, then U, then J, and finally 5. In this coding, 6 means 6 times the noise, E stands for 14, Q for 26, U for 30, J for 19, and 5 for 5. The highest point, U, marks a signal 30 times stronger than the usual background, a spike rarely seen in years of survey data. The telescope's receiver, split into 50 channels, each 10 kilohertz wide, was tuned to 1,420.4556 megahertz, the hydrogen line, a frequency chosen for its physical importance across the universe. The WOW signal appeared in channel 2, isolated to just that one slice of spectrum. The printout also includes the sky coordinates, right ascension, 19 hours, 25 minutes, 31 seconds, and declination, minus 26 degrees, 57 minutes, placing the event in Sagittarius. The entire event lasted the exact length of one beam crossing, matching the telescope's fixed drift scan mode as Earth rotated. Jerry Eman, reviewing these numbers days later, circled the sequence in red and wrote his famous exclamation. No other logbook from that week, nor any subsequent scan, has shown a comparable pattern. The numbers are precise and unresolved. 4 features set the WOW signal apart from the millions of routine blips that crossed Big Ear's printouts. First, the signal's strength, peaking at 30 times background noise, stood out as an unmistakable spike, not a statistical fluke. Second, its bandwidth was remarkably narrow, confined to a single 10 kilohertz channel. Most natural sources, like pulsars or interstellar gas clouds, produce broadband emissions that spill across many channels, but this event left a sharp vertical trace. Third, the frequency landed almost exactly at 1,420.4556 megahertz, the hydrogen line that astronomers consider a universal marker for interstellar communication and a protected band for radio astronomy. Fourth, the signal's shape matched what a fixed, distant source would produce as it drifted through the telescope's beam, rising, peaking, and falling across a precise 72-second window. Despite these hallmarks, 2 decisive absences cast doubt. No repeat signal ever appeared, not in the second beam that swept the same sky minutes later, nor in more than 50 targeted attempts by the Ohio State team in the following months and years. International observatories, including Arecibo and the SETI Institute, later scanned the coordinates with even greater sensitivity. All reported null results. No astronomical object, satellite, or terrestrial transmitter has ever been linked to the coordinates or frequency. The WOW signal remains a one-time event. Its narrow band profile and hydrogen line alignment fit the criteria for an artificial source, but the lack of repetition and corroboration leaves the evidence stranded, strong yet isolated. Each effort to repeat the detection has only sharpened the puzzle, forcing astronomers to confront the limits of single-event data. Antonio Paris, an astronomer from St. Petersburg College, offered a natural explanation in 2016 that briefly captured headlines. He argued that the WOW signal could be traced to the passage of Comet 266 P. Christensen, or possibly P 2008Y 2 Gibbs, whose hydrogen-rich Comet might emit faint radio waves at the hydrogen line. Paris and his team observed several comets in 2016 and 2017, detecting weak emissions near 1,420 megahertz, and noting that 266 P's position in August 1977 loosely matched the WOW coordinates. The idea seemed to offer a plausible, if unglamorous, answer: a comet's drifting hydrogen cloud passing through Big Ear's beam. But the numbers do not add up. Big Ear registered a peak flux density of over 2,000 Janskis during the WOW event, a value that requires a dense, compact source. Peer-reviewed models of cometary hydrogen emission, based on known production rates and coma sizes, predict signals at least 200 times weaker than what was recorded. Even under generous assumptions, the hydrogen envelope of 266 P would fall short by orders of magnitude. Spectral analysis deepens the mismatch. The WOW signal was confined to a single 10 kilohertz channel, while cometary hydrogen clouds produce broader, fuzzier lines, often spread across 5 to 25 kilohertz or more. No comet observed in the decades since has produced a signal with the same sharp, narrow profile. Other hypotheses have been scrutinized just as closely. Terrestrial radio interference, for instance, typically leaves telltale sidebands, or harmonics, which are absent in the WOW data. Known sources of radio frequency interference also tend to drift in frequency or repeat, neither of which fits the 72-second one-time spike. The interstellar cloud model, another candidate, fails on bandwidth. Natural hydrogen clouds emit too broadly, lacking the WOW signal's crisp spectral edge. Each proposal meets the same fate. No natural or terrestrial source, when measured against the data, satisfies all the constraints. The WOW signal remains a singular event, precisely recorded but still unexplained. CHIME, the Canadian Hydrogen Intensity Mapping Experiment, began scanning the northern sky in 2018 with a fixed array of 4 massive cylinders and more than 1,000 dual polarization receivers. Within months, its wide field of view and high cadence revealed a new kind of radio anomaly, repeating fast radio bursts, or FRBS, with unpredictable patterns. But in late 2019, one source stood apart, cataloged as FRB2018-0916b. This object produced clusters of bright millisecond-scale bursts that followed an unmistakable rhythm, a 16.35-day cycle, with 4 days of activity followed by 12 days of silence. Over 3 years, CHIME and partner telescopes logged more than 200 bursts, each confined to a narrow frequency window between 400 and 800 megahertz. Localization efforts, combining CHIME's array with very long baseline interferometry, pinned the burst to the outskirts of a galaxy called SDSSJ0158 00.2 8 plus 6 542 53.0, roughly 500 million light-years away. The FRB's projected position sits about 250 parsecs from the nearest young stellar cluster, ruling out a direct association with massive star formation. Dynamic spectra show that The bursts arrive with a dispersion measure of about 349 parsecs per cubic centimeter, confirming their extragalactic origin. Fluence measurements reach up to 10 Jansky milliseconds, with peak flux densities in the range of 1 to 10 Janskys, well within detection limits for modern arrays, but far above typical galactic background noise. Despite this clarity, the physical engine behind the periodicity remains unresolved. Theories include a precessing magnetar, a neutron star in a binary orbit, or a lighthouse-like jet that sweeps our line of sight every 2 weeks. No model fits all the observed properties, and no electromagnetic counterpart such as X-rays or optical flares has been found. What sets FRB 20180916b apart from single-shot anomalies is the sheer volume and precision of its data. Each burst's arrival time, frequency drift, and polarization are cataloged in detail, offering a rare chance to test astrophysical models against repeatable evidence. The result is a signal that is both well characterized and deeply puzzling, pointing to gaps in our understanding of extreme cosmic environments. Continuous high-sensitivity surveys have transformed the hunt for unexplained signals. CHIME's architecture, 4 fixed cylinders lined with over 1,000 receivers, monitors the northern sky every day, capturing transient events that older telescopes would have missed. Its wide field of view and uninterrupted coverage allowed astronomers to log hundreds of bursts from FRB 20180916b, mapping its 16.35-day rhythm with a precision impossible in the era of single-pointing instruments. Each new burst is time-stamped, measured for fluence and polarization, and added to a growing database, creating a foundation for testing competing theories. This shift in observational strategy is not just about catching more signals, but about fundamentally changing what can be learned from them. Where the Big Ear's drift scan mode offered a single 72-second glimpse of the wow signal, modern arrays like CHIME deliver a continuous stream of data, revealing patterns and cycles that would otherwise remain hidden. Survey design now prioritizes dwell time, cadence, and sky coverage, maximizing the odds of capturing both rare one-off events and periodic sources. Looking ahead, the Square Kilometer Array, called SKA, promises another leap. When fully operational, SKA will scan the sky with roughly 50 times the sensitivity of today's best arrays, covering frequencies from 50 MHz up to 15 GHz. Its sheer collecting area and digital processing power will allow astronomers to detect signals far fainter than those seen by CHIME or Arecibo, and to localize them with sub-arcsecond accuracy. The engineering community behind these instruments is not just building bigger telescopes, they are redefining the boundaries of the observable. Each new array brings the possibility that a wow-like anomaly, or a new class of repeating burst, will be captured with enough detail to finally move from speculation to explanation. Science still faces 2 open cases, the 72-second 6EQ-U-J5 anomaly and the FRB 20180916b, with its 16.35-day cycle. No natural or artificial explanation commands consensus. As new telescopes like the Square Kilometer Array come online, the real question is not what signals exist, but what evidence can truly illuminate their origin.